Greetings out there in video land. Rusty and I have rested up from the video series on the Supro amp build and thought it might be nice to produce a video that explains probably the most basic of all the components in an amplifier circuit. Let's face it, just because a component is basic doesn't mean that it's all that easy to understand or that it is widely understood by all people. I know it's a topic that's been flogged to death, but let's try a different approach today. Okay, I, like you, get really tired of hearing things either not well explained or explained in ways that make no sense or have no practical application. Well, we're going to change that today. So sit down, grab your popcorn, and get ready for an explanation of resistors and how you can use that knowledge practically in fixing, building, and designing amplifier circuits. Now, as we will see, resistors are very dynamic devices. They require a flow of current to function. Let's begin our visualization of how resistors work by using these diagrams based on the analogy between the flow of water and the flow of electrons in an electric current. And in my analogy, we're going to have the river here, and the resistor is going to be a dam with a passage through the dam of varying diameters to allow water to pass through. We will see that the larger the passage or hole in the dam, the less resistance it presents to the flow of water, and the smaller the hole in the dam, the more resistance it will provide to the flow. Okay, the analogy then will begin with a moderate to high current river. We will build the dam across it, and in this case, with a very large passage for water. In other words, this is a low resistance dam. And we see that the water flow after the dam is about the same as the water flow before. We see there's very little difference in pressure before the dam or after the dam. So the low resistance dam results in a current flow that's barely altered and almost no difference in pressure on the left side and the right side of the dam or resistor. Now, we have the same river that we saw up above, but when it encounters the high resistance dam, we can see that the water current or electrical current is nearly stopped. So the current flow after the dam is quite low compared to the current flow before the dam. Also, there is a tremendous pressure differential. You can imagine the water pressure building up behind this dam is going to have a great deal of pressure against the dam face, and that is what we equate to voltage, because voltage is electrical pressure. So the voltage on this side of the dam, or pressure, is much, much greater than the voltage or pressure on this side of the dam. Next, let's look at the possibilities that can occur when we are dealing with a wire or a river that is carrying very low current. When we apply resistance to the low current and we apply a very low resistance, the opening is such that the change in current or the change in pressure on either side of the dam is virtually invisible. It's almost non-existent. There is some response to any resistance, no matter how low, but it becomes almost infinitesimal when you get down to very low resistor values. Next, let's see what happens to our low current river or wire when we apply a moderate to high resistance. In this case, although the passage would be very small for a high current line, with the low current line, it's really relatively not that small, and we end up with very little reduction in current and very little change in pressure or voltage on either side of the resistor. Now let's take a look at the third possibility, in which we install a very, very high resistance across the low current wire or river. As you can see, the hole is quite small, and it does have a noticeable effect both on the current on either side and also on the electrical pressure or voltage drop on either side of the resistor. So it should be noted that it's going to take extremely high resistance, say on the order of 500K to 1 meg ohm, to have a noticeable effect on a low current line. So let's review real quickly before we move on. If we have moderate to high current and apply resistance to the flow of current, we find that with low resistance there's almost no change in the flow of current or in the pressure difference on either side of the dam. When we apply high resistance to that same moderate to high current flow, we see there is a huge difference both in current flow and in pressure, electrical pressure and water pressure on both sides of the dam. When we have low current, it almost doesn't matter how much resistance we apply unless we get to really high resistance. Otherwise, we'll have virtually no effect whatsoever. So based on what we've just seen, I think we can say that the effect on current and pressure change that we will see both in a river with a dam or in an electrical circuit with a resistor is directly related to the amount of current that's flowing in the river, or the number of electrons or electrical current that's flowing in the wire, and secondly, the size of the hole that we make in the dam, or the amount of resistance that we place in that wire. Since that's a big mouthful, let's boil it down to shorter phrases. We can say that the pressure change on either side of the dam or resistor is equal to the amount of current times the size of the hole in the dam, which we know is the resistance. The smaller the hole, the larger the resistance. The larger the hole, the smaller the resistance. Now let's take it to even simpler terms, because it's always better, I think, to boil things down to the simplest form. It makes them easier to understand, as long as we know where those simpler terms came from. Let's call the pressure change on either side of the dam the V for voltage drop. In other words, the pressure is going to drop, isn't it, from the left side of the resistor or dam to the right side. And we can say then that the pressure change, which we've already agreed occurs, is a result then of, and instead of the amount of current, let's just write an I. That's the traditional symbol for current, times R, which is the traditional symbol for resistance. So V equals I times R. Now, if that sounds familiar, that's Ohm's Law. Okay, we've all heard about Ohm's Law, and I imagine that a bunch of people had no idea really what it was or what it means. Now you see where it comes from, and also I'm going to show you in just a minute some very practical applications in your amp circuit and your circuit design to understand Ohm's Law, and it will allow you to make all sorts of very useful calculations and save you a lot of time if you try to resort to trial and error to come up with values. Now let's alter our formula to isolate one of the other variable values on the left, which sounds all scary, but being an algebra teacher, I couldn't resist. Let me start off here with the one we just came up with, V equals IR. This will tell you what the voltage drop is across a resistor if you know the current and you know the resistance. But what if I want to know the current flow in a wire? I don't know that current flow, but I do know what the voltage drop is across a resistor, and I know the value of a resistor. This is the same formula as this, but it's just been transposed in a way that I'll show you in just a minute. So if I want to know current, I'll use this formula. If I want to know voltage drop, I'll use this. And third, if I want to pick out a resistor to achieve a change in the flow of current, or a change in voltage on either side of the resistor, then I'll use this formula, R equals voltage divided by current. Okay, so this one will tell me the resistance I need, this will tell me what the current flow is, and this will tell me what the voltage drop is with certain different resistors and different currents. Now, for those of you who have some mental block about algebra, get over it, okay? You probably encountered algebra in high school and you were probably trying to score some beaver shots or else concerned about the zit on your forehead or something like that. Well, we don't have that problem now, hopefully. So let's be grown-ups about this and let's look at a little algebra and see where these formulas came from. Now let's see how I get these two formulas. I'm going to start off with V equal IR, which we've already derived. And there's a rule in math that if you have a equation like this and you do the same thing to both sides, you don't change the equality. So let's divide both sides by R. If I divide by R over here, the R's will cancel. And then I'll end up with V over R equals I. Or I can transpose and say I equals V over R. To get the third formula, same rules. Divide both sides by the I, or current, and I get V divided by I equals IR divided by I. The I's cancel, and I end up with V over I equal R, or transposed R equals V over I. I'm sorry if that sent any of you into seizures or gave you flashbacks to Mrs. Feeney's algebra class, but I think really a review like this every once in a while is kind of helpful, and I hope you feel the same. Now, what makes all this worthwhile is we're going to discuss some practical applications. The older I get, the less time I have for just nonsense and theory. And I want things boiled down to what good does it do me to know this? So we're going to solve three different problems with an amplifier circuit. Number one is one I think we're familiar with. What is the plate current in any tube? It doesn't have to be an output tube. It could be your first preamp tube. Well, one of the beauties of tubes is the cathodes, in almost all of them, have a resistor, a cathode-bias resistor, to ground. Now granted, the output tubes in some amplifier circuits have grounded cathodes, and alternate means are necessary to determine the plate current in those tubes. That's explained in some other videos that I've made. But for this presentation, let's just consider the 90% of all the tubes in any amp which have cathode bias resistors. If you want to know the plate current in that tube, in other words, I want to know the current if I already know the voltage and resistance, I'm going to use this formula. And it should also be noted that anytime I am looking for or using current in these formulas, it's always expressed as amps, not milliamps, but as whole amps. So for this determination, I will use the formula I in amps is equal to voltage drop divided by resistance. I don't know these values yet, but I'm going to find them out. And here's how. With the amp completely off and electrolytic capacitors drained, you clip your ohm meter on either side of your cathode bias resistor and measure the resistance accurately, say to 1 or 2 decimal places. In this case, I measured this one and it's exactly 1,000 ohms. Then you switch your meter to DC volts, turn on the amp, and measure the voltage potential or the voltage drop on either side of the resistor. Your meter will do this for you automatically. You just clip onto either side, and the reading you get, which in this case, I got 35 volts. So there is a differential in current or voltage on either side of this resistor of 35 volts. From here to here, 35 volt difference. So I write that down. Now I'm going to divide 35 volts by 1000 ohms. I get 0.035 amps. Remember, this is always in amps, or 35 milliamps. You want to see change amps to milliamps, you just move the decimal 1, 2, 3 places to the right. So 0.035 amps turns into 35 milliamps. This is how the plate current is determined whenever you're biasing your output tubes. And it can also apply to any tube in the amp that has a cathode bias resistor. Okay, my next inquiry. What's the current anywhere in my circuit? Pick out any spot in the circuit and you're wondering, what is the current here in this particular area of the circuit? Well, just find the closest resistor, and let's look at our diagram here. Our power transformer puts out our AC high voltage. The rectifier turns it into DC high voltage, which we call the B+. And anywhere in the circuit where there is a resistor, we can measure the voltage drop across the resistor. In this case, I'm looking at the what they call the power supply rail, or the first output that I get from my rectifier. Now I want to know, what is the current coming out of my rectifier? And I think this would be fairly useful information. I'm going to take my readings just like I did in inquiry number 1, and I'm going to turn off the amp. I'm going to drain all the electrolytic capacitors, and then I'm going to clip on my ohm meter on either side of the resistor and determine its exact resistance. In this case, I did it and I found it was exactly 100 ohms. Then I switch my resistor to DC volts, turn on the amp, and measure the voltage drop across the resistor. In this case, I did, and I found it was 10 volts. So I then will divide, according to my formula, my current in amps will equal my voltage drop divided by my resistance. I got 10 volts voltage drop, 100 ohms exact resistance, which comes out to 0.1 amp, or I move my decimal 0.3 to the right, and I get 100 milliamps are flowing out of my rectifier, and that is the extent of my B+ current. Okay, our third capability using Ohm's Law is one that's of great use to those who are trying to design their own amplifier circuits. I think anyone even vaguely familiar with the power supply of amplifiers knows that you have the power transformer putting out AC to the rectifier turns it into high voltage DC, and let's say it's putting out 350 volts of positive direct current. Okay, that's our B+. And it's flowing at 100 milliamps. I know that because I've used my ability as demonstrated in inquiry number 2 to determine what is the current output from my rectifier. But in this case, I need 200 volts DC for my preamp tube plates. Now I've got 350, that'll fry them. I've got to reduce it to 200. How can I do it? What size resistor do I need to place here? Well, I think you can guess. We're going to go back to our preceding page and pick the formula that tells us resistance if we know the voltage and we know the current in amps. In this case, I know that I want to go from 350 volts DC down to 200. What's the voltage drop? 150 volts DC. So I plug that in as the voltage drop here. V is voltage drop, so I put in 150 volts here of DC. And secondly, what is my current flow from my rectifier? Well, I used method number 2 and I found out that it was 100 milliamps. I plugged that in, and remember it has to be an amp, so it's 0.1 amp. I divide and I come up with 1500 ohms resistance here. Will change the 350 volt DC B+ from the plates of my output tubes into 200 volts DC for my preamp plates. Well, that's about it. for today's video. Granted, there were no grand unveilings or demonstrations of tremolo, but I really think that basic videos like this will help build your foundation of knowledge and help you to solve the problems with your amplifiers, to adjust your own bias, and to even design your own circuits. I hope you enjoyed it and that it was informative and that you'll join us again for our future videos. Thanks so much for watching.